Hi, here we are discussing about a project, design and implementations of a low complexity continuously variable digital filters using a novel Farrow Equivalent-Newton structures based on a fractional delay filter. Here, the continuously variable digital filters are essentials in applications such as a software-defined radio, biomedical instrumentations and adaptive signal processing systems where the bandwidth must be tuned dynamically without redesigning the hardware. The conventional variable digital filters based on a Farrow or Newton structures offers either high performance or reduced complexity, but not both simultaneously. The major limitations of this design lies in the high power consumptions and the hardware overhead when implemented on FPGA platforms, which restricts their suitability for portable and low power applications such as ECG signal monitoring. To address these issues, this work presents a lower power continuously variable bandwidth filter based on modified Farrow Equivalent-Newton structures that maintains the desired flexibility while minimizing the hardware complexity. In the proposed architecture, a fixed FAR filter design using a frequency response masking technique in sequence in between two fractional delay filters realized through the FEN structures to further reduce the power consumptions and energy dissipations, and conventional irreversible multipliers are replaced with a reversible array multiplier constructed which using Feynman and Tredkin gate based designs. Okay, novelty of this proposed designs lies in integrating a reversible logic within the FEN based CVBF framework to achieve low power and tunable filtering, also suitable for real-time ECG signal generations and denoising applications. The development systems is modulated in Verilog HDLs and synthesized on Xilinx FPGA platforms. The performance evaluations confirms a significant reductions in the number of multipliers, lookup tables and DSP blocks compared to the conventional Farrow and Newton structures, along with a low power consumptions and improved signal fidelity. Now we can verify the paper. So this paper is fully designed for the continuously variable digital filters. It will be designed using 4 structure. Okay, so here the third order Farrow structure for realizations of an FTF. Okay, so here this one it's look like as the same FIR filters. Okay, but here the Farrow structures will be integrated with the same functionality. Okay, so each box it will be come with the delay additions. Okay, and only the mu part it will be multiplied with the end of the architectures of this block. Okay, so here finally it will be taken as a yn of the design. Okay, so this designs will be integrated in Verilog HDLs and synthesized in Xilinx Vertex 5 FPGA. Okay, so first of all we will verify this design. This is the Verilog HDL code for this design, and this is the simulation results. Okay, so filter input and filter output, and this is a synthesized design for this Farrow third order FTF filter reversible logic. Okay, so here LUT it will be take for 203. Okay, and this is the RTL schematic for this design. Okay, Farrow structure based FAR filter. Okay, and the next one is this one, nth order Newton structure for realizing FTF. Okay, so it's also look like the FAR filters, but it will be come with some divisions. Okay, that is a shifting method. Okay, so it will be handled in 1/2, 1/3 and 1/n part appeared in this architectures, and the multiplications coefficients we need to integrate with this design. Okay, so this designs code it will be integrated in Verilog HDLs, and this is a simulation with the ECG modulations. Okay, and this is a synthesized design. Okay, and then next it will be come with the FEN structures. Okay, so this is a FEN structures. So using this FEN, the future design we plan for the CVBF. Okay, so here y of n is an input and y of n plus mu is the output of this designs. Okay, so here the mu it will be integrated for multiplications purpose. Depends upon the mu it will be filtered, and the mu here working as a attenuations. Okay, and then we need to filter it for all the dB level. Okay, so here the dB mu level it will be given with 0.5 to 0.9 in the range here. okay, as per the paper designs. Okay, so this design also implemented with the Verilog HDLs, and this is a simulation result for this design, and this is a synthesis report. Okay, so here it will be take for 304 number of LUT. Okay, and the final proposed design is CVBF designs. Okay, that means a continuously variable bandwidth filter. It will be designed using FEN stretches, Farrow Equivalent-Newton stretches. Previous design, right? The same designs it will be constructed here, but additionally there will be added some architectures here. After that, they will be taken as a final output. And this is a simulation results for this design. Okay, filter input and filter output. Okay, and this is a proposed CVBF designs. Okay, it will become with LUT 531. Okay, so this overall proposed technique. Why? Because we have developed this one in choosing a array multiplier. So that array multiplier constructed with the reversible logic. Okay, and adder also it will be constructed with the reversible logic. So ripple carry adder, right? So it's also designed with the full adders is full adder Fredkin-Feynman gate, and the reversible array multiplier is also designed with the full adder Fredkin-Feynman gate. Okay, so here this one. Okay, so this is a design, 2 half adder based Fredkin-Feynman gate. Okay, so this all the method comparisons it will be updated here. Okay, so this is a comparisons table. So previously we verified the array multiplier comparisons with using a reversible logic, and this is a complete comparisons. Okay, so Farrow stretcher based filter, conventional array multiplier, and reversible array multiplier, and Newton stretchers, and FEN stretchers, and CVDF stretchers. Okay, so finally we written an abstract document for this project. This is a title, base paper, objective, and proposed title, proposed abstract, and existing system. Okay, and related notes with the disadvantages and proposed systems. Okay, and VLSI related notes, and the literature survey. Okay, finally come with the references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.